Hello everyone, Mae Govanen, Ienethnin Gilrandir. I am Gilrandir, and in this video I'll be exploring the constellation of Ursa Major. While Ursa Major contains the 7 stars of the Big Dipper, there is also a lot more to it. It is in fact one of the biggest constellations in the sky, and because of that I'll be splitting it into 2 parts. This is part 1. I'll start right in with a 3-dimensional view of the constellation in order to see it as it really is in 3-dimensional space. The box we're looking at right here has its distance scale on the bottom marked in light years and a projection on the back to help relate it to the sky view. It contains the principal stars of Ursa Major and that they appear to be clustered together towards the front of the box. This is partly an effect due to the greater distance of the furthest outliers. Eventually, I'll be including a total of 21 stars between both this video and part 2, but in part 1 I'll be covering the 4 nearer stars plus the Ursa Major moving group. Zooming in somewhat on the inner crowd, we get a better sense of the spaciousness between them. There was also enough room in the second box that I could label each star with its name, and we can see here that several of them are still clustered together, and this is real. These 5 stars are part of the Ursa Major moving group. It's a stellar association, which is a type of loose star cluster, and the closest one to Earth. A stellar association is generally considered to be the remnants of a star cluster that is drifting apart. The stars in the group still share a common motion through space, but they are gradually growing away from each other. For the Ursa Major moving group, in addition to the 5 members we see in the Big Dipper, there are half a dozen other stars in the region which are known to be members of the moving group. Although I'm not including them in this particular survey since they're not part of the sky pattern for Ursa Major, and I'm limiting myself to that pattern for the time being. Along with the Ursa Major moving group, there is also an Ursa Major stream. These are stars showing a space motion similar to the moving group, but more widely dispersed in space. It's generally thought that the stream stars had also previously been part of the cluster and have now drifted even further apart. Now I'm going to look at the distance table for Ursa Major. This shows not only the distance from Earth to each star, which is the top row, but also the distances between each star and every other star included in the survey. On the table, the numbers along the diagonal are generally the smallest, while those in the corner are largest. It's due to the diagonal generally following the path outward from Earth from nearest to farthest. There are also several smaller numbers within the Ursa Major moving group, with Mizar and Alcor being only 1.2 light-years apart, and Alioth only about 4 light-years from each of them. And at 5.3 light-years, Alioth is also fairly close to Megrez. Also notable is the 5.2 light-year distance between Talitha and Sarir. Even though Talitha is closest to Alcapra in the sky, Alcapra is actually much farther away, being about 310 light-years from both Talitha and Sarir. Next I'll go on to the size charts. The first one shows the 4 star systems closer to us than the Ursa Major moving group, plus a few that are farther out, which I'll be covering later in part 2. The second one has the moving group stars. Both size charts include our own sun at the same scale, so they can be compared with each other directly, showing a wide range of size differences. They also show how the moving group is dominantly type A stars, while the other stars are of several different spectral types. Now I'll go on to look at each star system individually, beginning 29 light-years out at Alula Australis, the closest one. This is a quadruple star system consisting of a pair of main sequence stars, each of which has a red dwarf companion. The first image here shows the 2 main components and the orbit of the B pair around the A pair, with our solar system in the background for comparison. Since the closest approach in the orbit is still more distant than Saturn, there is enough room for each of them to have a smaller companion. The second image here is a close-up of the A pair showing the orbit of the red dwarf around its primary. The scale of this orbit is comparable to our inner solar system and would not allow for any planets around either of them. My usual habit is to make a sunset scene on an imaginary planet orbiting the star at the same distance as Earth from our Sun. Since that would not be a stable orbit in this case, this image is a view from the window of a spaceship stationed at Earth's distance. It shows the Type F primary with the red dwarf companion, and includes our own sun for comparison. Now we're looking at a close-up of the Alula Australis B pair. This is a much tighter orbit and would probably allow for a planet at Earth's distance. So I've made this sunset scene on an imaginary planet to get a feel for the two stars as suns. Next, we'll make the 21 light year trip from Alula Australis out to Sarir. This is a double star system with a Type F subgiant and a red dwarf. This first sunset scene is showing a dry desert world at the primary. In this case, the two stars are very far apart, approximately 3 times as far as Neptune is from our Sun. This is a distance comparable to the Oort cloud in our solar system. Because of the distance, the orbit is expected to take several centuries, and since measurements have only been taken since the late 1800s, there hasn't been enough time for a good determination of orbital parameters. However, there is plenty of room for an imaginary Earth distance planet around each of them. And the second scene we're looking at here shows a cold, icy world at the red dwarf. Moving over toward the right, another 5.2 light years, we come to Talitha. This is also a quadruple star system, and it's particularly interesting because it has an unstable orbit. It consists of a pair of red dwarf stars circling around each other. Then this pair orbits a Type A primary, which has its own white dwarf companion. Currently, the red pair's orbit around the primary is highly elliptical, and when they reach closest approach, their orbit around each other will overlap with the white dwarf's orbit around the primary. Sooner or later, this will completely disrupt the orbits of all the stars, throwing them into a completely new configuration. We don't know what Talitha will look like after that. The instability of the current orbit is also an indication that there must have been some interaction between the stars in the past, throwing the red dwarf pair into its current high eccentricity orbit. They surely couldn't have formed in their present configuration, but we don't know what their original configuration was. The first sunset scene I have here is for the primary, with a more or less Earth-like imaginary planet, and the sun of that planet being somewhat larger than our own. To add to the mystery of Talitha as a whole, we don't have a spectrum for the white dwarf companion of the primary. I am presenting it as a Type G in this video, but that is merely guesswork on my part. The scene we're looking at now is for the white dwarf, and the imaginary planet is essentially a barren world with some large patches of ice on it. The two stars of the red dwarf pair are very nearly identical, so I'm using this sunset scene to represent both of them, with a more or less Mars-like imaginary planet. Departing Talitha now, we'll move on out to 23 Uma, another 34 light-years long. Here is a double star system with a Type F primary and an orange secondary. This pair is very widely separated, so much so that no orbital motion has yet been detected. This is what we call a common proper motion pair. Two stars that are traveling together in space, so we think they are gravitationally linked together, but so far apart we haven't seen any orbital motion since they were discovered. For most common proper motion pairs, this was no more than around 200 to 250 years ago. The sunset scene we've been looking at here is for the primary, with a barren, hot imaginary planet. And here's the sunset scene for the secondary component, with an imaginary planet showing an essentially subarctic climate. Now from 23 Uma, let's head back left toward the Ursa Major moving group. The first stop will be Merak at 13 light years from our previous location. This is the sunset scene for it. Merak is simpler, being a single star, a Type A subgiant. I also think it's worth noting that in the original Star Trek series, Merak was given as the location for the episode The Cloud Minders. Now we'll continue along the same direction another 8.3 light years to Phecta, the next star in the moving group. We're looking at the sunset scene here, and it's very similar to Merak. Also a singleton type A star, very nearly the same size. Moving along another 6.1 light years through the moving group, we come to our next stop at Megrez. Megrez is also a type A singleton, this one just a little bit smaller than Merrick and Fecta were. Now going on through the moving group another 5.3 light years, we arrive at Alioth. Another type A singleton. This one is rather larger than the three we looked at previously, and here we're watching it set over a desert landscape. This is the last of the singletons in this video. When we move on another 4.1 light years through the moving group, we arrive at Mizar. This is another quadruple star system. It consists of two pairs of type A stars, and they're in a common proper motion relationship with each other. They're too far apart to have shown orbital motion yet, but they're traveling together in space. So what I'm showing are the orbits of each pair. The orbit of the A pair is comparable to that of Mercury in our solar system, but that's too wide to allow a planet at Earth's distance to have a stable orbit. So what I'm doing again is looking through the window of a spaceship at Earth's distance from the primary. Now over at the B component of the Mizar system, this orbit is comparable to Venus in our solar system, and again, a planet at Earth's distance would not have a stable orbit. So once again, I'm looking through a spaceship window at Earth's distance to see the two suns next to each other. For the last entry in this video, it's only a short hop of 1.2 light years over to Alcor. This is a double, and the two stars are in a common proper motion relationship, so no orbit has been determined. Here is the sunset scene for Alcor Primary. It's a pale blue type A star, scene setting over a mostly ocean planet. And this is the sunset scene for Alcor Secondary. It's a type M red star, which is listed in the catalog as a main sequence, but a main sequence type M star should be a red dwarf, considerably smaller than our own sun. Now, when I run the numbers to compute the size of the sun, it's coming out a little bit bigger than Sol. So after triple and quadruple checking my calculations and still getting the same results, I'm kind of coming to the conclusion that it probably ought to be listed as a subgiant in the catalogs rather than a main sequence. This is as far as I'll be going for part 1. It's covered the Ursa Major moving group and 4 nearer stars, looking at the constellation three-dimensionally with a brief glance at each star individually. And I'll move on farther out in part 2. I hope you found this worth a few minutes of your time, and Naigilgalad Uiven Men, may there always be starlight on the path.